Well, then I'll just yell. Anyhow, thank you for inviting me. I'm pleased to be here. It is, in fact, not hotter in Baltimore right now. But, hey, that's no one's fault. And I was going to make some political joke, but I will just pass on that. Good. So the work I'm going to be talking about the origin of large-scale magnetic fields, is work where I've collaborated with my former graduate student, who's now a postdoc at Johns Hopkins, Amir Jafari. And I thought I would start out the talk with a picture of a large nearby star that some of you may recognize. The little white lines are post-processing addition of magnetic field lines. So it's not, even in the X-ray, a totally honest picture. OK, what's the problem I want to talk about today? How large-scale magnetic fields grow, what sets their saturation limit. This is traditionally called the large-scale dynamo problem, as opposed to the small-scale dynamo problem, which is when people worry about how energy gets diverted into magnetic fields with a chaotic structure. The generation of large-scale magnetic fields is a process that takes place in many different systems in the universe: stars, galaxies, accretion disks, planets. I'm not going to say anything about planets. People do computational simulations of the process. Sometimes they're encouraging, sometimes they're disappointing. There are challenges in numerical simulations of the dynamo process, which have not been completely overcome. There are also laboratory experiments to look at the dynamo process, which produce confusing results that do not resemble what we were expecting to see by analogy with astrophysical objects. So basically, the generation of large-scale magnetic fields is a process that takes place in a turbulent medium, and it's the generation of structure on scales much larger than the turbulent eddies. There are other examples of such processes. Here's one hitting the southern coast of the United States. I forget which hurricane this was. The way this is supposed to work in astrophysical objects is illustrated here. This is not my diagram, okay? But it has the essential points. Imagine, if you will, you have a star envisioned here as a beach ball with vertical magnetic lines indicating a poloidal field up here passing through it. Only the internal structure includes differential rotation. The field lines wind up, and they wind up. And here we just consider the toroidal field generated by all the winding up. And imagine, as a second step, that we convert them into spirals with systematic sense of spiraling along the field lines, presumably imposed by the turbulence that the field lines are embedded in. And then if we reconnect all these little loops that form along the spirals, we can reinforce the large-scale magnetic field. So that's...
Quick question. If you had a consistent spiral, that would have a topological charge associated with it, which you're going to get.
Right. So as Chris was just helpfully reminding me, the step from here to here is kind of amazing, because you go from these nice regular lines that have no twistiness to them, and suddenly they all have twistiness. The way, when this theory was first formulated, back at this point 6 or 7 decades ago, people just envisioned that the magnetic field lines are arbitrarily thin little things, and you can fold them in a consistent spiral just by forcing them around. But magnetic field lines, well, as a mathematical idealization, they're not like that. As a physical manifestation, they're definitely not like that. They're more like ropes. Okay? And if you take, I brought along a topologically charged line here, and the time reversal of that process, making the straight lines into curly lines, would be to take this and, without moving the ends, eliminate all the twistiness, which, as we all know, is the wrong way to do it. And if you really want to do it, you just let go of one end, and you go like this, and you expel the helicity off of one end. The problem is magnetic field lines just go on forever, and you can't expel the helicity. So this diagram has a cheat embedded in it. You can do this mathematically. If you have a highly conducting fluid, you rewrite the induction equation by remembering that the electric field is minus the V cross B. And so the induction equation has this simple form where plasma physicists of any modest degree of competence could rewrite this equation by including a bunch of neglected terms here and here, which would stretch on for a page or two. But we can ignore these in astrophysics. They're small scale, minor effects. The fact that they are small but not zero is extremely important. But, well, the point is the fact that they're small but not zero means that you can meaningfully talk about averaging over magnetic field lines and reconnect them, and you don't have to imagine that the field lines are exact things. This equation implies what's commonly known as flux freezing, where if you have a ball of plasma or any astrophysical fluid, the magnetic field through it is frozen into it, and consequently it's like having a bunch of unbreakable threads threading your volume. So the little bit of non-zero resistivity is necessary so that the threads are not unbreakable and you can reorganize them. Now, how do you make a dynamical model out of this equation? You use mean field dynamo theory. You break apart the field into a large scale piece and a small scale piece. The small scale piece is on the scale of the turbulence. The large scale piece is on the scale of the system. This is actually a crude way of doing it. Obviously, you can define a sliding range of scales, but this gives you the essential flavor. And then you write the induction equation like this. And is this a pointer? No. OK. I'm just going to wave. So the evolution of the large-scale field, denoted by the capital B, is the advection by the large-scale velocity field, the stretching by the large-scale velocity field, and then the curl of an electric field, which is due to a fluctuating velocity and a fluctuating magnetic field. Basically, eddy scale effects are promoting a systematic electric field. So advection, stretching, and the coherent electric field that somehow appears in all these separate little eddies. This piece, let's see, the stretching is the bit that differential rotation was doing for you in the picture. And this piece is the magical moment when the field lines suddenly became replaced by spirals. So what is that piece, the electromotive force? People have defined this in contradictory, tried to evaluate it in contradictory ways, but I think the cleanest thing to do is to just say, if you have some systematic effect that's driving V cross B to be non-zero, then it will drive V cross B to be non-zero, but the turbulence will make it relax back to zero on a correlation time. So you have this equation, and that was first pointed out by Bouquet, and that allows you to evaluate V cross B as time derivative of velocity cross little b times a correlation time, velocity cross time derivative of b times a correlation time, and you can turn the crank. I don't want to talk about the algebra of this. You get a bunch of different kinds of contributions. You get a piece which is proportional to large-scale magnetic field and the coherence time, and the current helicity minus the kinetic helicity, or the twistiness of the magnetic field minus the twistiness of the flow lines. And then you get some other terms which we don't have to worry about right now, drift terms and dissipative terms. So the current helicity as a pseudoscalar, the thing that enters in here, is the dot product of the current and the magnetic field. It is related to a conserved quantity. It has traditionally been treated as a damping term, something that imposes a back reaction, which I think is exactly wrong. And the kinetic helicity, that's the twistiness of the flow lines. And in traditional mean field dynamo theory, that's how you get a spiral field line, is that the flow spirals around. And in experimental attempts to replicate large-scale dynamos in the laboratory, people try to force the flow to have a non-zero kinetic helicity. The kinetic helicity is not a conserved quantity, not related to a conserved quantity. It has to be imposed by the environment. But there are plausible ways that that would be imposed in a star. In any case, that's the term that traditionally has been taken to be the driving term for dynamos. What is it? It's a pseudoscalar. That means that if you reverse parity, turn all three spatial directions around, it will switch sign, even though it's just a scalar. In order to get it to be non-zero, you have to have symmetry breaking in all three spatial directions. So up, down, in and out, right, left. In a differentially rotating star, the differential rotation breaks symmetry in two directions, and then the vertical structure of the star breaks it in the third direction. When you do that, you get an estimate for its size like this. This is velocity squared. This is the size of the object, like a star. And this is a measure of the importance of rotation or shear in the system. This is the eddy turnover time again. So this is dimensionless. And in an accretion disk, we have an internal instability of the magnetic field. This thing is basically 1. This height, this length is the height of the accretion disk, and you get this expression here. So you can see this quoted all over the place as reasonable estimates. What's the current helicity? Oh, that didn't quite work out. Excuse me. I didn't fix the animation there. So the contribution to the electromotive force from some pseudoscalar current helicity, I've given it here. You can't just change the current helicity around because it's related to a conserved quantity by the wave number of the turbulence squared. So it's basically in any environment more or less a constant that you multiply by. And this thing is a matrix that takes it from a scalar to a tensor. What is this? This is like in phase space, it's a unit vector in the wave vector direction. Or if you like, it's k vector over k. I think as a spatial transform, it's called the Riesz transform. Anyhow, it's dimensionless, and you get large components when the eddies are very narrow along that axis. Now, how about that pseudovector? Pseudoscalar. The magnetic helicity, A dot B, is a locally conserved topological quantity. It seems weird because it's gauge dependent, so it's actually a whole family. But for our purposes, which is to say tracing what the current helicity is, if you impose the Coulomb gauge in regular conditions at infinity, it's a nice, well-defined quantity. It is an example of a Chern-Simons symmetry. Simons is, of course, the guy who made a huge amount of money in the hedge fund business and endowed this institute in New York City. It is, as far as I know, the only classical physics example of this kind of symmetry. You can see this kind of thing pop up in quantum field theories all the time. It measures the twistiness of the magnetic field, and the important thing for us is that it tells you what the current helicity is doing, and you can't get rid of it. You can only move it around. If we divide it into a piece due to the large-scale field and a piece due to the small-scale field, then we get a modified conservation equation. Here's the flux, the divergence of the flux. So this is just like any other conservation equation. Here's dH dt. And now we have a term that breaks conservation. This is the term that corresponds to taking the twistiness on small scales and putting it into large scales, or vice versa. It's the transfer rate between scales. And the important thing to note here is that this transfer of magnetic helicity between scales is the parallel component of the electromotive force, exactly what you need to drive a dynamo. So mathematically, what this is telling you is, this equation tells you why, in the cartoon at the beginning of the talk, you had to make the field lines into spirals in order to create large-scale field. Except, the part where you made them into spirals was magic. But what followed from that was perfectly sensible. I should add, there's a piece in this which is proportional to little h. So if you ignore the right-hand side, you get a relaxation rate for this to drive to 0. This is like, well, you probably can't even see this. I've overused this slide. Anyhow, this is the Alfvén frequency squared times the correlation time. It's usually pretty fast. Now,
Wait a minute. If JH vanishes, say, across the boundary of your domain, doesn't that mean that the volume interval of little h is conserved?
yes.
So then how can you have relaxation?
So I said dH dt, I'm sorry, dH dt relaxes to 0. I didn't say h relaxes to 0.
Can this destroy the large scale field if some of the dynamo reverses?
Yeah, there's no time asymmetry imposed at this point. You could be killing the large scale field. Now, if there is no right-hand side to this equation here, if this flux is 0, then what that tells you is that if you try to drive a dynamo, you accumulate magnetic helicity which turns the dynamo off. That is, that relaxation time is the time for zeroing the dynamo process. This was pointed out by Gruzhinov and Diamond back in 1994, and it's essentially a no-go theorem for trying to drive a dynamo by pushing the field lines around. What it tells you is that relatively rapidly, and long before the large-scale field becomes very strong, the process dies. So the first thing to remember about magnetic helicity is that it turns off kinematic dynamos before they do anything terribly interesting for you.
One could say you're partly setting up a straw man, although this is getting into what I'm sure you're going to talk about, which is that the Babcock-Layton model, going way back, involved transport of magnetic flux tubes across the surface of the sun.
Right. So you don't actually need to do that.
Violates the assumptions of this no-go theorem.
Yes. So there's a school of thought, which people have pushed pretty hard in the last 20 years, that the answer to this is to move the magnetic helicity across the boundary. And I'm not saying that doesn't happen. I'm saying that's not how dynamos, that's not necessary to drive a dynamo. So what is the magnetic helicity flux? Okay, so formally this is what it turns out to be. I don't know if this is all this enlightening to see this. This is the shear, and this piece here, this expression can be non-zero if the turbulence is anisotropic and it's in the presence of shear. It does not depend on the correlation time for the turbulence or even the existence of turbulence. It corresponds to if you have a bunch of field lines and you sort of shear them, just like if you were taking a rope and you were turning the middle, you would make a magnetic helicity flux because you drive spirals in opposite directions. So the way to think about this is, suppose you had these field lines fixed at some point and you sheared the middle, you'd accumulate magnetic helicity at the fixed points. This is a purely turbulent piece. To first order, it looks like 0. This is the usual electrostatic potential. But we can estimate what it actually naturally turns out to be by looking again at a system where it's being systematically driven by the effects of rotation and turbulence away from zero, and then it tries to relax back. And that allows us to balance it. And it's a long, long, hideously complicated calculation. But for this discussion, we just need to notice that dimensionally, it's got to have a certain form. It's got to be v squared times b squared times the shear or the rotation times the correlation time squared. This is all dimensionally determined. And then there's a geometric factor which has to do with whether the eddies are sort of isotropic or close to isotropic, or whether they're severely distorted. And in general, that's a factor which is less than 1. So in slowly rotating, nearly isotropic turbulence, you can just let this be 1. An important thing to note about this is that I've written this b squared. This is the small scale fluctuating magnetic field squared. This flux does not depend on having a large scale magnetic field. It's completely, it's not 100% insensitive to that, but it is dominated by a term which is insensitive to that. So if you have a rapidly rotating star, the shape factors are important. This is a pseudo-vector. That is to say, if you do a parity transformation, it does not reverse direction. In a thin disk, like a galaxy or an accretion disk, it will point along the vertical axis, which is the direction of the available pseudo-vectors, rotation and shear. Or shear is not a pseudo-vector. Rotation and local vorticity. Same thing. So probably also true for a galaxy. If you have more complicated geometries, you can get pseudo-vectors that are pointed in all kinds of different directions. They don't have to be aligned with the local vorticity or the rotation. Okay. What does this do for the electromotive force? Well, first of all, simple question. If we can estimate the magnetic helicity flux, we can ask how long it is before the accumulation of magnetic helicity produces a current helicity, which is more important than the kinetic helicity. And the answer is it's about 1 eddy turnover time, which is the shortest time scale you can talk about in a turbulent model like this. So what this tells you is that the kinetic helicity term is never important. It's not just that kinematic dynamos don't take you very far. They're not realistic models of dynamos and astrophysical objects. So the second effect of worrying about magnetic helicity is that there is no kinematic dynamo in astrophysics. There's a long literature up to the paper by Gruzhinov and Diamond, which appeals to kinematic dynamos. There's a long literature after the paper by Gruzhinov and Diamond, which simply ignores their work and appeals to kinematic dynamos. None of it actually applies to real objects. Okay, all right, I'm sorry. I'm probably getting carried away with equations here. Allowing for the fact that you can accumulate magnetic helicity, this gives you a corrected electromotive force which accounts for that back reaction. And it has this form. This is the term induced by having magnetic helicity flux. And you will notice that it scales as 1 over the large scale field, which is kind of weird. It implies that this term is enormous if the large scale field is very weak. What's going on there? The answer is, I got this equation by assuming there was a balance. The magnetic helicity flux piles up magnetic helicity, the divergence of it, and then interaction with the large scale field takes it away from small scales and puts it on large scales. So if the large scale field is infinitely weak, that second part doesn't happen, and the magnetic helicity just piles up. So this is assuming that that process is working, and what that tells you is that the electromotive force becomes stronger for weaker large-scale fields. And then all the other terms in the electromotive force having to do with the kinetic helicity, dissipation terms, or whatever, they all get a projection effect, which depends on eddy shape through this matrix R, which eliminates part of their effect. So you can think of it as something that takes dissipative terms and replaces them with drift terms that do similar kinds of effects, and suppresses the kinematic effects altogether. And you get a growth rate for the large-scale dynamo out of this, which is, in the end, proportional to the geometric mean of the rotation and the shear times the correlation time. The strength of the fluctuating magnetic field, fluctuating velocity field, divided by the large-scale magnetic field and the size of the system. So generically, what this tells you is this kind of dynamo is not an exponentially growing process. It's a process that starts out fast and slows down. So when people talk about, say, the evolution of galactic magnetic fields from some early time when there's no large-scale magnetic field, what this tells you is that the galactic magnetic fields grew fast and more slowly as time went on, and they're now growing, if at all, at the slowest rate they ever have.
This question might be a little bit in some people's minds. I mean, what do they define what you mean by dynamo?
So what I mean by dynamo is that if I filter out, what I mean by large-scale dynamo, is if I filter out the largest spatial components of the system, how do I describe the growth and decay of those field components, which are on scales much bigger than an eddy scale? And people usually talk about the dynamo problem in terms of growing these fields, but of course, these dynamics can also describe their decay. So the third effect of what magnetic helicity does is it gives you a self-consistent large-scale dynamo that depends on shear and turbulence and grows non-exponentially. If you compare it to kinematic dynamo estimates, when the field reaches equipartition with the turbulence, it's growing at roughly the rate predicted by kinematic dynamo theory. But at all earlier times, it was growing much faster. So in accretion disks, little footnote, the turbulence is driven by magnetic field instability. When the magnetic field is weak, the scale of that turbulence is smaller. So in this case, there's actually an agreement between this model and the kinematic dynamo model in the qualitative sense.
Well, that's what another question about raised, which is that in the accretion disk, the shear is thin. It's much stronger than the internal stress, hydrostatic stresses.
Well, no. In an accretion disk, the eddy correlation time is about like the inverse of the shear.
Okay. But what I'm getting at is that it's kinematic. The MRI is kinematic in the sense that the orbital shear is always much stronger than the internal.
Oh yeah, no, but I mean, but the effect on V cross B is not actually kinematic.
Right, you're right.
But the
It cannot be understood.
yeah.
Got it.
Okay, so so when does this fail? Well, it doesn't fail because the kinematic dynamo dominates. It does fail when, as I mentioned before, when the large-scale magnetic field is very weak. And then the magnetic helicity just accumulates locally. Little dH dt is not zero. In a system, in a turbulent system, what's going on in that case is that you generate a large-scale field from the long wavelength tail of the turbulence, and it grows randomly over time. And that may eventually be important. Also, this theory ignores points in the final, well, in the saturated dynamo structure where you have magnetic nulls, And there is no large-scale magnetic field locally. It's a zero crossing of the field. And in that case, of course, you couldn't be efficiently coupling the magnetic helicity and transporting it to large-scale structures. And so if you just use the terms I've already described, you would predict that there was an infinite accumulation of magnetic helicity at those points, which is ridiculous. And the answer is that I've left out a term in the magnetic helicity flux, which is proportional to the gradient of the magnetic helicity flux. There's turbulent transport locally. So instead of getting a ridiculous singularity of magnetic helicity, you have a term I've neglected in the magnetic helicity flux expression, which is proportional to the gradient of magnetic helicity, which tends to move the magnetic helicity out of those points. But it doesn't really affect anything else. There's another way that it fails altogether, which is suppose you have a very slowly rotating star. Then the magnetic helicity flux is weak. The growth rate is slower. So there are really three rates which come into this, three time scales. There's the dynamo growth rate, which depends on what the large scale field is. There's the turbulent transport rate across the whole star, which smooths everything out and kills any dynamo. And there's the rate at which the magnetic helicity will accumulate if it's not being aliased up to larger scale structures. And those three rates become comparable at some low rate of magnetic helicity flux. And below that, there just is no large scale dynamo in a star. So this tells you that if you have a sufficiently slowly rotating star, the dynamo process will fall apart. This is not a novel prediction, actually. Kinematic dynamo theory also predicts this. This mechanism is systematically more robust than the kinematic dynamo, but it still tells you that a sufficiently slowly rotating star will not make a dynamo. I know there are those who argue that the sun is, in fact, close to that rotation rate, approaching it from above. So, we can get some insight into all this if we make a toy model. So, stars are geometrically complicated. Let's just make a dynamo in a box. It can be a periodic box, so we're not even losing magnetic helicity across the boundaries. Turbulence in a box, impose some shear. The dynamo will grow rapidly in the box. The magnetic field will grow rapidly because the dynamo will be working, but the dynamo will slow down as the magnetic field becomes strong. And there's some constant rate of turbulent mixing across the box. So at some point, the field will be strong enough that the dynamo rate will fall below the turbulent mixing rate, and the process will stop growing. So you can use that to estimate generically what does a saturated magnetic field look like in this case. Or since we've thrown density out, let's just say the Alfvén speed, the magnetic field divided by the square root of density. So for a slow rotator, slow in the sense that the rotation rate or the shear is small compared to the turbulent eddy turnover rate, this gives you this prediction. It's proportional to the size of the system and the geometric mean of shear and rotation. Now, in fact, stars are stratified. Convective zones vary in their properties throughout. Some zones are more important for this process than others. Like generically, the bottom of the solar convection zone is better at this than the top. There are other effects going on. Magnetic buoyancy will tend to lift the field out. Turbulent pumping will push it back down. So the box size is not really the size of the star. It's really like the pressure scale height times some factor of order unity. Let's skip that. A few complications. Suppose there's a strong background field, and it's so strong that it actually competes with the turbulent field. Does this change the process at all? No, because it turns out that what you get is something that looks like this b squared, little b squared, but it's a component of the large-scale field squared. It's the k parallel wave number of the turbulence times b squared over k squared. But if you're being driven by convection, this thing is always the convective growth rate. So if this becomes very large, this becomes very small. And consequently, driving up the magnetic field may change the detailed prediction of the magnetic olicity flux, but it doesn't change anything qualitatively. If you have strong rotation and shear, then the dynamo process depends on a combination of shear and rotation. The transport of magnetic olicity flux will be dominated by rotation, and the shear, of course, is dominated by shear. So in the end, the saturated field that you get in this case is like the pressure scale height divided by the eddy turnover time times the ratio of shear to rotation to the 1/2. This thing is more or less the convective velocity. So this predicts an energy density which is like the turbulent energy density times the factor of order unity, which is the ratio of shear to rotation. So if you have really rapidly rotating stars, what this tells you is the magnetic energy density is like the convective energy density. Which is kind of cool. It's telling you that in that limit, the magnetic energy density is limited by the energy of the turbulent cascade, even though the energy being directly pumped into the magnetic field comes from the differential rotation of the star. Of course, the differential rotation of the star comes from the convection, so it's not really paradoxical. But in terms of this model, it's a little funny. The magnetic luminosity of a star, the non-thermal radiation generated by the ejection of magnetic field, is then going to scale with the convective flux of the star, which is its total luminosity. So in this limit, you expect that activity above the star is going to be scaling with the luminosity of the star for rapid rotators. Now, I stole these graphs, of course. You can ignore this one. But this is an attempt to plot rotation rate in non-dimensionalized units. So these are slow rotators. These are fast rotators. This is X-ray luminosity as a fraction of bolometric luminosity. It's a well-known result. You get a steep rise here, basically proportional to the square of the rotation rate. And then it flattens out for rapid rotators, and it's pretty flat. So this is in accordance with the predictions, generic predictions of this Dynamo model. Here you see the same thing. These are for low luminosity stars, by the way. But this now shows, instead of the X-ray activity, the deduced magnetic flux deduced from Zeeman splitting in star spots on a distant star. So you're taking, if you take this as a measure of the buried toroidal field in the star, you see that the toroidal field in the star is scaling linearly with the rotation rate. These are slow rotators, these are fast, and then levels off. And you get a more or less constant but messy graph to the left. So, bottom line, very simple generic predictions from this Dynamo model explain what you see in main sequence low mass stars. It's not the same thing as having a detailed Dynamo model for the sun. For example, if you ask me why the sun has an 11-year cycle, based on this, I would say, I would actually have to have a model of the sun to give the answer to that. But the sun, like all these other objects, does follow this general pattern that you predict from this model without having a detailed model. I should say that stars with strong magnetic activity lose angular momentum efficiently and slow down. So any individual star will tend to move across this diagram and down. And eventually, we'll hit a point when the dynamo stops working.
Where's the sun on the diagram? If it were, but
Yeah, the sun is around here somewhere, I
Getting
think.
close to Rossby unity.
Yeah, maybe around here.
So you say basically that the dynamo theory really involves calculating both the magnetic field and the differential rotation. of the
Yes.
system.
Yes, and I haven't even tried to do the differential rotation thing here. But obviously, for a complete model of how a star behaves, you have to be able to do that. I've just taken it as a given.
Well, we published two papers, but they were roundly ignored.
I have to go back and look at them now, because the bottom line here is, so far at least, I have simply treated the differential rotation in a star as something that God hands down on tablets with Moses. Probably the world doesn't work that way, but what can I say? I'm getting pretty short on time here, so let me just make a, yes?
Don't the magnetic field lines work to resist differential rotation?
There is some back reaction, and of course, you would have to have that included in the model. In the sun, what we see is in the course of the magnetic cycle, you can see some small effects, whether the magnetic field is strong or not on differential rotation. So yeah, it's being driven by convection, but there is some feedback. Whether or not that feedback ever dominates the differential rotation, I don't know the answer. It doesn't in the sun, but so let me say a few words about accretion disks, and then I may just have to wind it up. You can apply this kind of reasoning to accretion disks instead. Now, accretion disks are different because in stars, the turbulence is driven by convection, but an accretion disk is driven by an instability of the magnetic field. And what happens if you look at a power spectrum of the turbulence in a magnetic field, in an accretion disk, and compare it to the power spectrum of the magnetic field, you see that the magnetic field has a long wavelength bump, and then a turbulent bump that matches the kinetic distribution. And the MRI is taking the first long wavelength bump and regenerating the short wavelength parts. But they're not at very different scales. And the rotation, the dynamo you get, of course, occurs on all scales larger than the eddies. So it works best just a bit larger than the eddies, and worse as you go to larger scales. The resulting turbulence is very anisotropic. So waving your hands and giving simple dimensionless arguments is not a great idea. You expect the magnetic helicity flux to be vertical. If the vertical wave number is very large, if the eddies are very flat, then the magnetic helicity flux is very ineffective. So one way you can arrange for that to happen in a simulation of an accretion disk is to turn off gravity. The MRI likes to be as flat as possible. It will be as flat as possible. The dynamo will turn off, and depending on your resolution, you will get a weaker and weaker saturated level of magnetic field in your simulation, which you do. Presumably the way to cure that is to put in vertical structure, and that seems to cure it. And you get the expected generic result, which is the Alfvén speed grows to some fraction of the disk thickness divided by the correlation time, which is like some fraction of the sound speed, but not a big fraction. I tried taking a simulation of an accretion disk by Shane Davis, and we did some averaging, not entirely arbitrary division between large and small scales. And this is a graph of the current helicity and the magnetic helicity times a constant compared to each other. So you can see that they do track one another extremely closely. But if you look at the electromotive force, the results are much less impressive in the simulation. I mean, they're correlated. You might not want to write home about that correlation, but it's there. So basically what this tells you is that the expected dynamo effect, expected in this model, is seen in the simulations, but it's not a really strong correlation. If you threw out the magnetic helicity terms in the expression for the electromotive force, then asked how well would you do without them, you actually are negatively correlated. So there is no superior model waiting behind. What's going on here? Well, so the basic problem is that in order to really do a realistic astrophysical simulation of a dynamo, you need to conserve magnetic helicity pretty damn well. Now, obviously, if you have high enough resolution, everything that should be conserved is going to be conserved. But we don't have arbitrarily good resolution in any real simulation. Next best thing is if you have a spectral code. So you're in Fourier space most of the time. That does generically a much better job at conserving magnetic helicity than a grid-based code. But that makes it very hard to include vertical structure in the accretion disk. So if you're trying to simulate a dynamo in an accretion disk, you might worry that you're not conserving magnetic helicity very well. And you're going to do best when the eddy scale is close to the box size. So for a simulation of accretion disk, that means you're going to do best when the magnetic field is at its strongest. And as the magnetic field goes through weak cycles, which it does, you're going to do very badly. And we see this in change simulations, is that the magnetic helicity conservation is mediocre but not negligible in the high states of the magnetic field. And when the magnetic field falls to a low state, there's no conservation of magnetic helicity at all. It's just a series of random numbers. Because the eddy size is very small, and the numerical effects wipe you out. I might add that you also have a global problem, which is that I just told you that if you made the eddies very flat, magnetic helicity became poor, magnetic helicity flux became small, the dynamo became weak. Besides buoyancy, vertical stratification and buoyancy, another way to make the turbulent cells have a significant vertical extent is to have a vertical magnetic field. But the vertical magnetic field in an accretion disk can't be isolated at a single radius. That's a global problem. And so to the extent that this effect is important, you need to do a global simulation of an accretion disk. There's a paper I wrote with Amir showing that, in fact, accretion disks, once you put in all the dynamics, can successfully drag magnetic fields to small radii. So what you have is an environmental effect, which becomes very important at understanding the radius of the accretion disk at small radii. Okay. I'm not going to talk about galactic magnetic fields here because I've abused your patience too much. So in summary, if we completely ignore kinetic helicity and kinematic dynamos and just consider a dynamo driven by magnetic helicity flux, we get something that is qualitatively kind of amazing in explaining stars. The other route, as Chris mentioned, has been for people to think that there might be some way of driving a kinematic dynamo and then ejecting the magnetic helicity embedded in eddies out of the object. This quantitatively is extremely hard to do. I want to say impossible, but I would like to argue with an enthusiast for this approach first before I say it's completely impossible. But for various scaling reasons, I don't think it works. Because of the fact that we're using magnetic helicity as the driver of the dynamo, we don't have to worry about alpha suppression and all the no-go theorems that people have suggested. It does mean that experimental attempts to do a large-scale dynamo in a laboratory have to date been trying to do it all wrong, and their funny results stem entirely from that. They get rapidly oscillating fields. They do not get the kind of stable large-scale structure they were aiming for. That's because the way they're doing it is they're funneling your conducting fluid in spirals to make helicity. Numerically, it's difficult but not impossible to simulate a dynamo, but it means that you have to conserve magnetic helicity and test that you are conserving it on timescales longer than the dynamo growth timescale, which is a really hard constraint, and I'm not sure that there are codes that really do this well enough. You could try to write a code which explicitly conserves magnetic helicity, but since magnetic helicity is a non-local topological quantity, this is not a straightforward thing to do. Okay, I'm going to cheat here. I didn't talk about this, but I can make magnetic fields grow in galaxies very quickly when the universe is young. Or if you ram two galaxies together and screw up their magnetic fields, they should reorganize very quickly. And then I'm just going to end by saying there's no kinematic dynamo. All that stuff is wrong. Okay, that's the end.
So these magnetic dynamos take an existing magnetic field and amplify it. But where do you get the seed and magnetic field to start with?
Right, so you can use as a seed for the large-scale field the long wavelength tail of a turbulent magnetic field. But that just pushes the problem back one step, because you can then ask, why does a turbulent fluid have a magnetic field at all? So people have analyzed the small-scale dynamo problem where you start out with a turbulent cascade in a conducting fluid and ask, how does the small-scale magnetic field appear? The answer is that a fraction, a constant fraction of the energy in the turbulent cascade is converted into magnetic energy, so that, roughly speaking, there's a constant conversion rate of about, I want to say, I forget whether it's 5 or 6%. It depends on whether you believe the numerical simulations of Andrei Berezniak or Jun-Young Cho. There's actually an analytic estimate of 8%, but of course that's least credible. So the point is, if you start out with a field that's close to zero, not exactly zero, but close to zero, in a turbulent cascade, the turbulent cascade will linearly grow that field up to equipartition in about 20 eddy turnover times. You might ask, that's still not zero, your starting field. On scales so small that you're not in equipartition on the smallest scale in the turbulent cascade, the fields can grow exponentially on the turnover time of the smallest undamped eddies. So if you were to start out in the early universe with, well, let's just say when a galaxy is born, suppose you start out with 10 to the minus 21 Gauss, or 22 Gauss, it doesn't really matter which. The small-scale dynamo will get you up to about 1/10 of a microgauss in about 20 eddy turnover times for the turbulence in the disk. So the large-scale dynamo is really just about imposing spatial structure and lifting you out of that last bit up to several microgauss.
So it's always a dynamo, it's never like a built-in battery where you start at zero.
Oh, I'm sorry. Of course, when I say the early universe gives you 10 to the minus 21 Gauss or whatever, I'm implicitly saying there is some battery there. And there are a number of such batteries that have been proposed. Biermann battery, I think Soldovich proposed a photon drag on galaxy disks as they formed. There's an appendix in my dissertation where I talk about how sound waves in the early universe generate vertical motions. And Sabino Matarese pointed out that those vertical motions will in turn generate weak large-scale magnetic fields. All of these generate fields which depend strictly on known physics, but still give you extraordinarily weak magnetic fields in the early galaxy, but not zero.
But magnetic velocity is the large scale field. And you know transport of magnetic velocity across, or negligible transport. How do you get a field with this? I'm missing one.
The total magnetic helicity of the large-scale field is still zero.
Because you're taking the cancellation components.
Yes.
So you're having transport magnetic velocity across the equator in the interior. But that's an additional geometrical effect, which isn't in those equations, is it, in a transparent way? Or?
No, I mean, the magnetic helicity transport, well, it doesn't affect the qualitative estimate.
Well, I understand how you're getting order of magnitude estimates for various fluxes and so on. But
But if you want to make a model of what the sun is actually doing, you have to look and see.
I'm worried that somehow you're glossing over magnetic velocity as a global topological charge.
I don't think so. No, look, so you can do the problem in a box.
By assuming there's no transport across the boundary, yeah.
You can set up the problem in a box and make the whole problem completely analytic.
But it's insoluble analytically. I mean, to really go into the equations and actually solve them mathematically, that can't be done.
No, but you can solve the mean field equations.
Sure. But those don't concern magnetic velocity.
Well, yeah, they do.
How does the stepping mode operate for really small bodies like carnivores and primates as opposed to
So the reason I've tried to avoid saying anything about really small bodies is there comes a point where the resistivity actually could be important. And I don't have a good feeling for what happens at that point. So I've stuck here to cases where resistivity is not a major effect. It's not that the resistivity, say, in the interior of the Earth where the dynamo is going on, is directly important over the whole scale of the turbulent zone. It's that the Earth is a very fast rotator. And very fast rotators produce very narrow turbulent cells. And on the scale of those cells, resistivity could be important. So I don't want to commit myself.
But in the thin equation, what is the sign of the magnetic field? What motivates the alignment of the sign of the field?
In a thin accretion disk,
Like the galaxy.
like the galaxy, the physics would work exactly the same if you reverse the direction of the magnetic field everywhere.
But I'm missing exactly how the different angular rings of the thin accretion disk manage to communicate in such a way as to if your magnetic velocity plus is meant to be vertical.
So, right.
Coordinate.
This is an interesting problem. It's easy to see how annuli in the thin accretion disk generate large-scale magnetic fields. And for the point of view of angular momentum transport in the MRI, that's really all you need to know. But if you look at the galaxy, what you see is much more organization than that. Well, there are two ways that you can try to solve this problem. And so the hard way would be to say, well, there is more radial transport going on in the galactic disk than you're allowing for. Things go in, things go out. There's a lot of radial mixings, very anisotropic. That's probably true, but I don't know if that's enough. Another more straightforward point is to say, maybe the halo of the galaxy plays a large role in the dynamo, which is also not an original thought. But even if you don't have an ordered field in the disk, the magnetic helicity flow vertically is very ordered. The sign of it is fixed by the dynamics. So you're accumulating magnetic helicity of opposite sign in the halo above and below the disk. And if the halo is turbulent and it's also differentially rotating, the dynamo in the halo may actually be important, at least in the sense that it helps to organize the overall galactic magnetic field, which is actually my preferred solution because there is some evidence for a halo magnetic field, which is important.